I try to imagine a fellow smarter than myself, and then I try to think, what would he do?
Charge up your axons, ready your receptors, and shift your lobes into upper beta phase. You are listening to Smart Drug Smarts, the podcast dedicated to helping you optimize your brain with the latest breakthroughs in neuroscience, nootropics, and psychopharmacology.
Hello and welcome to Smart Drug Smarts. My name is Jesse Lawler. I am your host, and this is the 151st episode of this podcast dedicated to the ongoing betterment of your brain by any and all means at your disposal. In this episode, we're going to be talking about white noise, that random, hissy, staticky noise, which you're probably aware of, probably know for its sound muffling qualities, something kind of neutral you can play to drown out less neutral noises if you want to. But we're going to be talking in this episode about a recent study showing that it actually can have cognitive enhancing properties for the right type of person. We'll find out what that right type of person is in the main interview when we'll be speaking with Swedish researcher Dr. Sverker Sikström, and also learning a little about pink noise, brown noise, some of the rainbow of other random noises that are out there. Yes, there are actually quite a few. That'll be in the main interview. If you hang around for the very end of the episode in the ruthless listener retention gimmick, switching from something for your ear to something about the eye, you've probably heard the phrase, beauty is in the eye of the beholder. But according to a new study, it might also be true that cocaine is in the eye of the fish. What the heck am I talking about? You will need to wait until the end of the episode to find out. But first of all, let's kick things off as usual with This Week in Neuroscience.
Smart Drug Smarts, This Week in Neuroscience.
So keeping it on theme with this week's topic of white noise, wanted to talk about noise in general in This Week in Neuroscience, and particularly how it affects members of the animal kingdom. Humans are a pretty noisy species. That's probably a surprise to nobody, especially when we congregate in cities and have big machines and things that go on at all hours of the night, trash compactors and ambulance sirens and that beeping sound that the UPS truck makes when it backs up. All that kind of stuff can make human environments a loud place. But of course, human environments can also be desirable ecosystems sometimes for animals because we tend to keep big predators away, and oftentimes there's a lot of leftover food lying around. So many animals choose or are forced to put up with the noise, get on with their business, and adapt to the noisy human environment. Now, how a given animal species chooses to do this will vary from one animal to the next. While you might imagine that almost any animal would like some peace and quiet, many animals actually rely on sound to some degree as part of their feeding strategy, their hunting strategy, their mating strategy. Crickets rub their legs together, songbirds sing love songs, bats echolocate their next meal. So there's interesting questions that come up when human noise isn't just an environmental annoyance, but is actually something that's competing with the animals' need to produce their own noise to get their own work done. Scientists in Panama recently completed a study looking at the fringe-lipped bat, which is native to Central and South America and likes to eat frogs. Knowing this fact and knowing that the fringe-lipped bat is living increasingly in closer proximity with humans, the scientists developed robotic inflatable frogs to dupe these bats into hunting them under a variety of conditions. So they got a bunch of fringe-lipped bats, they got a large cage with microphones, hidden speakers, and a variety of robotic inflatable frogs. They actually look pretty good. I would have been fooled had I been a bat looking at one of these frogs. They've got a big inflatable throat, just like you'd expect in a frog. So they had this large cage and this assortment of fake frogs, and they set up the frogs so some of them were near speakers where a bunch of background noise could be played, and also some of them had physical blocking objects around them to mess up the echolocation of the bats a little bit. And also the robot frogs had their own speakers to play croaking noises, and then there were secondary speakers that could play environmental noises, the sorts of noises that would actually be in a Central American forest. And then there were still other speakers that would play distracting, sort of human-sounding noises of car horns or trash compactors or Britney Spears or whatever it is. And then they would set these bats to hunting under a variety of different sound conditions and see what sorts of robot frogs actually got attacked. None of the robots actually got eaten because robots actually taste pretty bad. So there's two ways to go about finding a frog if you're a bat. One is by echolocation, the high-pitched chirps that give a 3D rendering of the physical environment. And the second one is just by hearing, by listening, the type of auditory input that we as humans are familiar with. And both of these things can be giveaways if you're a frog. The bats can hear your croaking, and the echolocation is actually picking up on the bulge of the throat when it fills up with air before the croak happens. So in a natural auditory environment, both types of frogs, those that could be picked out auditorily and those that could be picked out through echolocation, they were hunted down by the bats in equal measure. But when the noisy fake human sound started being played over the speakers, masking the sound of the croaking, the bats were found to rely much more heavily on echolocation. They actually sent out twice as many echolocating chirps as they did in a normal sound environment. And the robot frogs that had been arranged to sort of give some cover against echolocation, those frogs survived much better in this artificially noisy man-made sound environment. So the bats actually performed pretty well in this experiment. They adapted, they changed their approach, and luckily for them, they're hunters with a couple of different hunting modalities. When a living thing has a fallback system like this, if listening isn't working, then I'll rely more heavily on echolocation. That sort of thing is called phenotypic plasticity, basically saying that the physical phenotype of the organism gives it some options as far as its behaviors. Other examples of animals adapting to human noise include songbirds that change the pitch that they sing at, and other types of birds that have just started singing at less noisy times of day. Nightingales, for example, appear to sing louder on weekday mornings than they do on weekends. So just a little sprinkling there of the effects of noise on animals. We will get to the effect of noise on humans in the main interview.
Smart Drug Smarts, the podcast so smart, we have smart in our title twice.
Picked up a couple of 5-star reviews this week on iTunes. They're both quick, so I thought I'd give you both of them. Mac Daddy R says, I've been enjoying 2 doses per day, 1 each way on my commute. Genuinely interesting, relevant, and entertaining. And Radaf22 says, amazing podcast. This podcast is both educational and entertaining. Well, thanks very much to both of you, and thank you to everyone, past, present, and future, who has left nice reviews for the podcast on iTunes or elsewhere. Spread us around on social media, name dropped us to your friends, any of that stuff. It is all very much appreciated. I am abysmally, shockingly, horribly late with the Brain Breakfast newsletter, which is now a couple of weeks overdue. I've actually got 2 or 3 half-written drafts that I have no good excuse for not having finished one, sent it out, but to publicly socially shame myself and make sure that I get one out in the next couple of days, I will make mention of our newsletter, The Brain Breakfast, which I try to get out weekly, but is not nearly as religiously scheduled as the podcast itself. If you want the opportunity to press reply and easily castigate me on email, then you can sign up for The Brain Breakfast by going to smartdrugsmarts.com/newsletter. Much more quick than I have been with The Brain Breakfast are the fine folks over at Axon Labs, where luckily customer service is handled by somebody other than me. Axon Labs is the retail wing of our operation here at Smart Drug Smarts. We got a couple of supplement stacks over there. Nexus, our cognitive stack based around aniracetam and CDP choline, and Mitogen, our mitochondrial stack that has got, among other things, sulbuthiamine and idebenone. We're going to be having an idebenone episode before too long here. That interview is actually already recorded, just need to get it published one of these weeks. You can find both Nexus and Mitogen online and the quicker than me service people over at axonlabs.io, or you can visit smartdrugsmarts.com and click on the shop link from there. I think we'll have some Halloween stuff going on the social media for Smart Drug Smarts and Axon Labs in the next couple of days here, so keep your eye on that. That is all the newsy, updatey stuff, so let's move on now to the main interview.
Smart Drug Smarts.
So several episodes back, we had an episode about synesthesia, where different senses seem to get entangled in a person's brain, leading to some interesting things for the people that experience synesthesia, being able to apply sensory attributes that we think of as being sort of isolated in one sense to something from another sense, like a particular sound might invoke a color, or a smell might have a tactile feeling to it, something like that. And that's always the first thing that strikes me when I hear white noise is, what about white noise makes it white? But maybe first of all, just to clarify what white noise is, here's some white noise. So it sounds like random noise, random static, but not all static is created equal. And interestingly, static can be very well defined, mathematically speaking. What you just heard in white noise was random sound with a flat, what's called a spectral density. So any given frequency that your ear can hear was equally likely to show up in that noise. There are also technical definitions for each of the following: pink noise, brown noise, blue noise, violet noise. So each of those have different and well-defined densities of the frequencies of sound in those sound waves. We're going to be talking about a study of white noise in this interview, but I felt like since we were on the topic, we might as well cover what all these noises are before we dive into what can they do for our brains. And we're going to be talking in this interview with Dr. Sverker Sikström from Lund University in Sweden. He is a professor in cognitive psychology in the Department of Psychology there, and has research interests ranging from the computational modeling of memory to using computer models to quantify the semantic content of all words in a language, to our topic today, looking at how noise can improve human cognitive performance. He has even developed an iPhone app, one called Smart Noise, based on the research that we'll be talking about here. So let's jump in with Dr. Sverker Sikström.
Well, actually, this whole research project started off with a total fiasco. There was this PhD student that was really in pain. He had set up this, he was a former teacher and he were interested in students in his classes that had poor attention, and he basically wanted to investigate how bad does it get if you put them in a noisy environment. So he had a strong hypothesis that if you take these people that in the beginning have poor attention and then you add noise, they will perform super lousy. And was he disappointed? Because the data didn't turn out at all as he expected. And at that time he had another supervisor, and he was like, maybe we should look at some other data or like leave this aside. And then we started to talk, and all of a sudden I kind of realized there are certain findings showing that under certain circumstances noise can actually be beneficial. Let's start to think about it. That's kind of where we started.
There's certain types of noise that one would think, like banging pots and pans or somebody playing random notes on a piano, that just seem almost so inherently unpleasant that it's hard to imagine that those noises could be beneficial. Like, what were some of the variables in the types of noise that you wound up looking at?
Yeah. So in the beginning, we made a theoretical distinction between noise, which is like a very purely defined concept, and distractor, which is more kind of messy. The nice thing with noise is that it's perfectly defined. When you say white noise with a certain decibel, then you know all the entities of this stimuli. Whereas other things that has some kind of information into it are more or less distracting. So we understood early on that it's noise that we're interested in, because noise gives like a background pattern of information, but doesn't steer your attention to something specifically. Mm-hmm. In comparison to like a distractor, it's like somebody opening the door and you turn your head and what's happening here, or somebody talks and you start to listen to it. But noise has no direction. It's smooth, it's continuous. It doesn't focus your attention away from something. It just kind of activates.
I guess like in the natural world, there probably are a lot of examples of that sort of thing that we needn't pay attention to. Like if you're on a beach, the sound of the surf, or in a windy environment, the sound of wind is like, it's not necessarily indicative of anything if it's a constant background.
I personally believe that there are many things that are kind of sufficiently noisy in the natural environment that we could call noise. And many of these natural phenomena, such as wind and oceans, waves, etc., are very noisy in its qualities. But the exact scientific definition of pure white noise is very specific, and that's only pure white noise. It's nothing else.
Right.
Actually, there's so many qualities that sounds can have or distractors can have. In our research, we haven't dwelt on what type of distractor there are, because there are so many variables you could play around with. So we would get lost into that.
For the noise non-specialists out there, of which I am definitely one, what is the technical difference in layman's terms between white noise, pink noise, these different colored noises?
When you have white noise, you have the same amount or loudness of noise in different frequencies bands. So it's the same loudness if you hear at high or low frequencies. Whereas this pink and brown type of noises either have lower or more level at higher or lower frequencies.
So would the white noise for a person be different than the white noise for a dog because they can hear different frequency ranges than we can?
Yeah, I mean, when we define noise in this way, it's a purely physical definition, and it's not necessarily tied to the experimental definition because, well, as you're hinting, we have a certain frequency band that we can hear sounds on, limiting the 20,000 K for young people and lower for elderly. So it's, in reality for us humans, it's a more narrow definition, I guess.
And so the results with humans, what did you find as far as the changes in cognitive performance? How did that vary, I guess, between different sorts of mental tasks that a person might have?
Yeah, so the general finding we had, the first experiment was like word recall performance. People listen to a set of words and then are asked to freely recall them afterwards. And what we found basically was that people with poor attention, they actually performed better in a noisy environment than in silence. So they had a higher score on the recall than when they were in a silent environment.
Yeah.
And noise was kind of large. It's like 80 decibel. It's like a vacuum cleaner. Like you're in a pub, you have to kind of talk aloud because there's so much noise in the background.
Yeah.
That type of noise we're talking about. And if you go down maybe below 70 decibel, then the effect tends to diminish a bit.
And I guess there's probably also an upper threshold. Like if you're in the turbine of a jet engine at 120 or 130 decibels, that would probably cease to be a good thing. But it was about
80 decibels sort of the sweet spot, or did you check enough of a range to have a sense of that?
Well, unfortunately, due to ethical reason, we couldn't put them in the jet engine.
Yeah, that's hard to get past an IRB.
Yeah, so we never tried above 80 decibel. It would actually be very theoretically interesting because, well, I haven't got into the theories, but one interpretation of theories would say that there's a sweet spot at some optimal sound. But we actually never have seen any experimental data that it's bad because you get too much auditory noise. So it's an empirically not answered question, and, well, we have difficulty of trying it out, basically.
I was thinking about this before we spoke and thinking about really silent environments, how if it's really quiet, sometimes you're afraid to make a noise yourself, and almost like a really silent environment heightens people's sense of anxiety. And I was wondering if maybe the opposite of that might also be true, if people tend to have their anxiety lessened a bit when there's enough of a noise to kind of provide some sound cover for their own activities. I mean, do you have any sense of that?
Well, when we say silence here, we talk about like everyday people silence. You're like in a silent room. Actually, few people have experienced silence in its pure sense, because in a normal environment, there are always some kind of sounds.
Right.
So you have to go to like a special room for that. And I've done that a few times in my life, and I get strange feelings in my gut being there, because it's like there's something weird. It's like you feel in your body that's what's happening here, because there's actually no sound at all. These are done in like normal silence, yes. Yeah. So, but of course, when you go down to like a normal silent room and somebody tries to walk across the room, then that sound would be very noticeable, of course. But it's not the noise makes other sounds, disturbing sounds, go away. It's not the case that is driving the effect, because the room is sufficiently silent to be silent. So it's not like it's stopping something else.
Were the people alone in a room, or like alone in a space, or were there other people there also? Was it like a social situation? They're
mainly conducted in a laboratory environment with an experimental supervisor taking control of this, but not in a crowd.
So what was the level of impact as far as the benefits that different people would see for being in this louder environment, noisier environment, I should say?
Well, first of all, we should clarify that. So you get this beneficial effect for people with low attention.
Mm-hmm.
Here we are mainly talking about self-rated attention. Do you have difficulty concentrating? You do this self-rated ADHD type of test. And those people benefit from noise. But we don't get this effect for people that experience themselves as being very attentive. They actually perform worse in a noisy environment. So there is this clear interaction effect between noise level and the overall general attentiveness. And I think that's interesting, because in one case, it kind of rules out alternative explanations, such as, this effect, of course, you perform better with noise because it's difficult to fall asleep. You just kind of wake up by it. But it doesn't account for that type of data. It would wake up people that have high attention as well, but it doesn't. They go down in performance.
These are self-reported performance. It's not objectively measured, I guess?
It's self-reported, yes. And we've done different studies. In some studies, we have, for instance, teacher judging their attentiveness. It works equally well. We have had people that are diagnosed with ADHD, and that works as well. So I think different measure of attentiveness has been successful.
What types of tasks were the people trying to perform? I guess just like garden variety example of what the memory task might be and things like that.
Yeah, so we tried on a different type of test, and we get, generally speaking, similar results. Over and beyond this vertical test, we also have spatial span, which means that a number of dots comes up on the screen, and you're supposed to press in the same order as the dot comes up, and then you increase the number of dots until you fail, and then we score the maximum number of dots you can recall.
Mm-hmm.
And then we also have continuous performance task, where you're supposed to press on a type of form, such as a square, but inhibit circles, and do it as fast, as accurate as possible. And most of the time, you use 3/4 of the times you press, and then you inhibit on fewer times. These three tests we've found beneficial effects on noise.
So how would somebody self-assess their level of ability to focus, ability to pay attention, and know whether noise might be something that they want to try? Or is it just something where everybody should try some white noise and see how they feel about it and sort of do the self-diagnostic?
Well, I think the first step would be, do you generally think that you have poor attention? And then if you answer that, maybe you should look further into this. But we actually developed a smartphone app is called Smart Noise that is iPhone based and anybody can download. And this actually provides a test for whether you benefit from noise. And it starts off with these self-rating questions. And then we also have 3 cognitive tasks you do either in silence or in a noisy environment. And then the app will tell you whether you benefit or not, basically. Over and beyond this, many people, after publishing this, many people has contacted us and say like, well, I'm happy to hear you studied because I've never been able to work or study in silence, and now everything makes sense when I hear this. Or some people can't even sleep in silence. So there's many like self-report of everyday people that knows this by experience. And I think most of us have a kind of a sense whether you want to have the radio on when you study or not.
What do you see as follow-up studies that you'd like to do? I mean, it seems like there's a lot of interesting potential follow-ups. What are you thinking about next?
One thing is that we want to make it more clear exactly what type of sounds are beneficial. And some years back, there was like this Mozart effect that people performed math tasks better in Mozart music.
Yeah.
And then there was a big debate about that and hasn't been able to replicate it. And we think this is simply occurring because they don't measure the level of attentiveness. And we don't get any effect of noise if you ask all the people the same. We only get it when we look at interaction with attentiveness. So I think basically you need that as a control variable. So I would like to see what type of sounds are sufficient to make this. Is it good enough with music or rain or whatever? I think that this could be a very interesting question to pose.
That's really interesting. Something you said a moment ago is that you need to have attentiveness as a variable in order for the signal to come through. Is that to say that for the people who find the white noise helpful, it's about the same amplitude of benefits as the amplitude of distractions that the people who find it unhelpful are? It's like the positive or negative basically balance one another out when you look at the population as a whole?
Yeah. Generally speaking, I would say that is the case. But it has been different in different studies. And in some studies, we get a general effect of noise, either positive or negative. But there's always this interaction that inattentive benefit more than attentive. Sometimes we get like a general decrease of performance or increase performance with noise, but you still get this interaction. So it could be a bit dependent on the exact setup.
What was the actual impact, the benefits that people saw?
Yeah, I would say like 10-20% increase in performance, relatively speaking, around that ballpark, I would say. Another thing, well, maybe you're going to ask this, but so far we only been talking about the experimental finding, but we also have a theory why this is happening.
Oh, well, that's great. I didn't assume that you necessarily had a mechanism of action pegged for this, but what do you suspect?
So this was actually kind of the idea that led me to start off with this research project, because earlier in the literature there has been this finding that's called stochastical resonance. Earlier this was only looked on a perceptual identification level. So you would, if you present a signal like a sinusoidal wave, for instance, and you're supposed to say, is there a signal or not? And it's really in a low, nearby threshold volume, then you actually hear better when you add noise. And this is a phenomenon called stochastic resonance. And the theory behind this is very simple. Basically, if you think about detection as passing a threshold, for instance, for a neuron to fire, you have to get sufficient input for it to activate an action potential to send out to other neurons. If the input is too low, so the cell is not responding either if in a signal or not, then when you add noise, then it is more likely to respond when the signal is on than when it's off. And the difference between probability of firing when you have a signal to when you don't have a signal is an indication of the signal. So basically, you can show, mathematically speaking, that adding noise in a threshold-based system is always beneficial if you have the right type of noise. So that is like a statistical theory that's very easy to simulate and think about, that we use as a theoretical framework for this. But prior to our research, this has only been done on perceptual levels, and we took it over to the cognitive level. And that meant that we went from like this hardly hearable noise to really high, like vacuum cleaner, like I have to speak to get through this noise. And the idea there is that we are interested in memory performance, and memory performance are in brain areas that is not normally working with detection, auditory detection. So in order for this auditory noise to penetrate into this brain area, you basically have to push up the volume, and then you get this moderate amount of noise in this relevant brain areas for memory. That's our theoretical reason why you need to have a high noise, and the reason for why noise in general is good. So that would in itself predict a general increase in performance by noise. But it doesn't provide a reason for why inattentive people perform better but not attentive. And in order to account for that, we need to add on another thing on this theory, and that is that inattentive people have another type of neurotransmitter system. Basically, it's known that they have a deficiency in dopamine transmission. And we argued that if you have low level of dopamines, that means you can think about this as a higher threshold. And when a threshold is really, really high, it becomes more and more important to add noise for it to pass. So that's the reason why it's beneficial for inattentive people. Attentive people have a low threshold, so it passes anyway. And adding noise when it passes is just disturbing the system.
Pouring water on a bucket that's already full.
Yeah.
Since you didn't know going into this that you were going to find a difference between these populations with higher or lower levels of ability to focus, ability to avoid distraction, what other variables were you looking for or asking about with your study subjects?
Actually, when I mentioned ADHD, it's actually not exactly what I should have said.
Okay.
It's more ADD. So it's the attentiveness that is the important variable. What we have found as not being important is the hyperactiveness.
Yeah.
Often people are both inattentive and hyperactive at the same time, providing the syndrome of ADHD. But some people are inattentive but not hyperactive. And it doesn't matter if you're hyperactive or not, you benefit from noise as long as you're inattentive. So it's the inattentiveness that plays part, but not the hyperactivity. We have been interested in electrical stimulation. So what we're trying to do is introduce noise in the brain, and earlier we have done that through the auditory modality. But on the other hand, it's not so fun having noise around you all the time, and it would be just even better if you could just introduce it without you noticing it. In one study that we recently published, we looked at introducing noise in the brain with electrical stimulation. So basically you put up 2 electrodes on the skull and you put a random current on there, and one in the left frontal lobe and one in the back of the head. And we have some data indicating that there's an interaction with attentiveness and the introduction of such neural noise that would be consistent with this auditory stimulation. So these are kind of a new field that we are moving into. So we are kind of planning on doing more of that.
It would also be really interesting to maybe have a test where you're posing questions to somebody verbally and have them looking at a field of essentially the visual equivalent of white noise, I guess just multicolored static, and see if that has any sort of effect.
Yeah, that's very interesting. We did some pilot study that's some years ago, but we never pushed it forward. So that's very interesting. Actually, I mean, you get this stochastical resonance phenomena in several modalities when we talk about detection of stimuli. It has been shown that, for instance, elderly people can keep their balance better if you stimulate the foot with the vibration. And also, I think the strongest effect of detection is in the visual modality if you add noise to pictures. And these are kind of unexplored phenomena in relationship to cognitive performance, whether these things could benefit that. So all of these things are interesting things.
Smart Drug Smarts.
So thank you so very much to Dr. Sikstrom for taking the time for that conversation. Really interesting there that it sounds like the research he described has kind of cracked the code at how to look at this data, that unless you also get information on how well the people are normally able to bring themselves to focus, the benefits or possibly the drawbacks of noise can kind of wash one another out, and you may not see the full impact of the results of white noise for certain groups of people. I think this would be a fascinating area for follow-up study, moving on from the premise that noise can have a beneficial effect to figuring out exactly what kind of noise for what kind of person, how to draw out the maximum benefits. Because it stands to reason that there might be a sweet spot. Also interesting what he pointed out, that they didn't find an upper threshold for volume where the results stopped being as good. That would be interesting if the dose response curve for beneficial cognitive effects actually peaked at a point beyond the safety or the pain threshold for human hearing. Just one of those things you'd like to see studied more. We'll definitely keep abreast of future studies in this area. And then moving on from mathematically defined noise, I mean, I still really like working with certain types of music playing. I find that to be a big benefit. But but being able to drill on exactly what types of music and kind of what the active ingredients are. Is it beat? Is it tempo? Is it the emotional content that's associated with that music? Being able to slice and dice those things would be really interesting. But now, moving on from sound to fish who do cocaine, let's listen to the ruthless listener retention gimmick.
Smart Drug Smarts, ruthless listener retention gimmick.
So we've talked about zebrafish before. Zebrafish are a favorite of scientists because they're small, they breed fast, they're cute. Actually, I don't know if cuteness really factors in, but they are. And they're also see-through. They have transparent skin so you can look right into them, see what's going on. Which, yes, they have scanning electron microscopes and things like that, which also allow you to see what's going on. But the transparent skin gives researchers kind of a live sneak preview, even before they slice and dice these little critters to see what various experiments do. And so oftentimes it turns out that zebrafish are used as animal models in studies when, for ethical reasons, it seems better to use a whole lot of fish than a whole lot of mice. There's sort of a pecking order, as you might imagine, in animal studies. When a lot of tests need to be run, a lot of animals might need to be sacrificed. You go for a paramecium before you go for a flatworm, before you go for a zebrafish, say, before you go for a mouse, before you go for a monkey. And this all kind of makes sense, but there's also the understanding that, at least if we're thinking that the studies might eventually be applied upstream to a human model, human physiology is a whole lot closer to a monkey than to a mouse, and a whole lot closer to a mouse than to something like a zebrafish. But the question is to what degree? And recently, scientists at EWAG, which is a aquatic research institute, teamed up with colleagues at Zurich University and looked at something that all of us are curious about, the accumulation of cocaine in fish. And they had done previous toxicology studies looking at how cocaine accumulates in zebrafish and saw roughly what they were expecting to see, which is that the cocaine accumulates in the head. This was assumed to mean it was accumulating in the brain, especially because at the early life cycle of the zebrafish, when they're often used for experiments, they have not yet fully developed a blood-brain barrier, so easier for things like cocaine to get into the fish's brain, in theory. But in this most recent study, the EWAG scientists used a new imaging method called MALDI-MSI to look in much finer resolution detail at exactly what's going on. So larval zebrafish were exposed to a defined concentration of cocaine for 8 hours. Then they were euthanized and frozen solid, and tissue samples just a few micrometers thick were then scanned by laser. This is the MALDI-MSI technique. And here's where things went sideways versus what the scientists were expecting. It turned out that cocaine was accumulating not so much in the zebrafish brains, but in the zebrafish eyes. The eyes were basically vacuuming cocaine up out of the fish's system like the most aggressive coke fiend that you could imagine. The eyes wound up with concentrations of over 1,500 milligrams of cocaine per kilogram of fish eye. This was between 4 and 5 times the amount found elsewhere in the fish, including the brain, and this is also an incredibly high density of cocaine in a live animal. In mice, concentrations 100 times smaller are generally deadly to the animal, and humans are even more sensitive, with just 0.1% the tolerance of the lowly zebrafish. Now you might say, how can the zebrafish do this? How can they possibly be taking in 1,000 times the concentration of cocaine that would drop a human dead and still swimming around behaving like zebrafish? Well, cocaine, it turns out, causes very different results in zebrafish physiology than it does in humans, or mammals in general. In mammals, cocaine is a stimulant, causes hyperactivity, and if you're a human, typically verbosity and a grandiose sense of self-importance, whereas in zebrafish, it is actually a motor depressant. It suppresses locomotor activity, so give cocaine to a zebrafish, watch it calm down. The timeline for washing cocaine out of the system is also very different between zebrafish and mammals. Because the eyes take up cocaine so greedily, it takes a long time for it to leak out to the rest of the bodywork and finally get expelled. 48 hours after cocaine exposure, 30% of that cocaine will still remain in the zebrafish's body. The takeaway from all this is that A, assumptions are dangerous. Unless they'd used this new type of imaging study to look in fine detail, they would have probably continued to go forward under the assumption that it was the brain, not the eyes, that was getting all this cocaine accumulation. And the larger point is, you really have to be careful on animal studies, not necessarily drawing inferences that the behavior of a compound on one animal is going to have much to do with how it affects other animals. Pretty much none of the findings of how cocaine affects larval zebrafish would transfer over to mice, much less to humans. And the opposite holds true too. Sometimes when we're thinking about environmental water quality, people might make assumptions about how certain chemicals are going to affect the water life based on what those chemicals have been seen to do in humans or in land animals or in a less appropriate animal model. Obviously, zebrafish larvae can put back a lot of cocaine, so while I don't think cocaine in water supplies is a big problem, this is an instance where using human models for data would probably make us be overly cautious if somebody were to dump cocaine in a local stream or something. Not that that probably ever happens.
We like to think of ourselves as a digital speakeasy for brain hackers, but you can call us Smart Drug Smarts.
Okay, you heard it. That is the very end of episode number 151. Thank you for hanging around with us the whole way through. If you enjoyed this episode and you want to spread it around, or even just check back on any of the links and things that we talked about here, you can find it online at smartdrugsmarts.com/151. Last week in episode number 150, we talked with Dr. Mark Mattson about plant-based toxins and why a little bit of a toxic thing might not be so bad for the brain and body sometimes, and it really is all about the dose. And next week, episode number 152 will be our Halloween episode, coming out, I think, the 28th, so a couple days in advance. I should probably tell you what the topic is, but I just can't do it. I'm going to keep you guessing. It's probably going to be a letdown if you're expecting something too Halloween-y, but it is both brain-relevant and scary. I think it's going to be a double interview, maybe even a triple interview, if we play our cards right. But you'll have to check that out here next Friday, same time, same podcast, and with the same unflagging commitment to helping you fine-tune the performance of your own brain. Have a great week until then, and stay smart.
You've been listening to the Smart Drug Smarts podcast. Visit us online at www.smartdrugsmarts.com and subscribe to our mailing list to keep your neurons buzzing with the latest in brain optimization. Smart Drug Smarts should be listened to for entertainment purposes only, although some guests on the show are medical doctors, most are not, and the host is just some random guy. Nothing you hear on this podcast or read at smartdrugsmarts.com should be considered medical advice. Consult your doctor and use some damn common sense before doing anything you think might have a lasting impact on your brain.